Welcome back, and this is the third in a series of video posts exploring diagnostic process mining. In the first two posts, we examined why identifying the true causes of problems is essential and how to define a problem properly. In this post, we'll aim to achieve three objectives. First, we will look to identify the various causal factors for a problem. Then we'll look at how we can specify the causal relationships between those factors. And finally, we'll examine how to estimate the effect of these causal factors on the problem. A brief reminder that this is the second in a six-step diagnostic process mining workflow. To begin, let's spend some time examining the meaning of causality. In other words, what does it mean when we say a certain variable X causes Y? To borrow a definition from the Book of Why by Judea Pearl, and I highly recommend that book, X can be said to cause Y if a change in X causes a change in the probability of Y occurring. Let's illustrate that. Say X is the average case complexity score and Y is the average cycle time. Then, if a higher case complexity causes longer cycle time, we expect to see cycle time increase as case complexity increases and vice versa. Notice the arrow from case complexity to cycle time indicating the direction of causality. However, if there's no causal link between two variables, say Z, the average height of a team, and case complexity, as we vary case complexity, we don't expect that to be a corresponding change in the average team height. We don't expect the team to grow taller or shorter on average. The question, though, is how do we identify the various causes of a problem of interest? I recommend doing this in a structured brainstorming session with subject matter experts. The output from this session is a list of all potential factors which may cause this problem. Let's illustrate this using the problem statement we defined earlier in the previous post. In case you missed that video post, we're investigating the lower than expected loan acceptance rate for a Dutch financial service company using the Business Process Intelligence Challenge Event Log from 2017. And on screen, you see the problem statement. Now, here's a list I came up with for that loan acceptance problem. I haven't got access to SMEs from that company, so I've had to come up with this list of potential causes on my own. The list is fairly self-explanatory, but let's highlight a couple of causal factors. There we see monthly cost. So the expectation or the assumption is that as monthly cost increases, the probability of accepting that offer will decrease. Another one here was the client offered an amount less than they requested for. If that was the case, then we assume the client is less likely to accept the offer than if they were offered an amount they applied for. If you have experience using a fishbone or Ishikawa diagram, you will find it helpful to use that tool in this step. It will provide the additional benefit that these causal factors will be assigned to the appropriate category. What's important, though, is that you have a list of potential causal factors. Next, we define the causal relationship between these variables using a causal diagram. There are two simple rules in drawing this causal diagram. First, if we believe that X causes Y, we draw an arrow from X to Y, as we previously discussed. The second rule is that we're not allowed to have direct or indirect cycles. In other words, a variable cannot cause itself. And this makes sense in the way that I cannot cause my own birth. Let's illustrate this. So variable x there causes a variable y, which in turn causes a variable z. That's acceptable. However, this is not acceptable because that's an indirect cycle, or this, where x causes z and z in turn causes x. As with identifying causal factors, I recommend you create a causal diagram in a structured brainstorming session. If you don't require any special tools, you can draw your causal diagram on a whiteboard, a piece of paper, or use tools such as Visio. However, I tend to use a web app called Dagity, and here is the URL for that app. I will also include a tutorial to how to use Dagity in the comment section of this video. However, suffice to say that this is my completed causal diagram. Notice the different colors. I'll explain what those mean later. However, before we conclude this section on causal diagrams, I'll briefly discuss three basic or atomic causal structures from which the more complex causal diagrams are built and the implications of this structure. The first structure we have is the common cause or the confounder. This is where a causal factor, in this case credit score, influences or causes other causal factors. So in this case, the credit score influences whether a customer has a competing offer from another financial service provider, as well as the monthly cost. We assume that a higher credit score makes it more likely that a client will have a competing offer from another provider and lower monthly cost, and vice versa. What's important to bear in mind is that these two variables will appear statistically correlated, as we explained in the very first post in this series. The second atomic structure is a mediator or a chain. In this case, we specify that the credit score influences the probability of a client accepting an offer through another causal factor, i.e. whether they've been chased or not. This variable chased indicates whether the company has repeatedly contacted the customer to obtain additional documentation, for example, to return the loan offer. We'll discuss this variable in more detail later on in this section. We assume that the company prioritizes customers to chase by credit score. So clients with a higher credit score are more likely to be chased than customers with a low credit score. And this in turn makes it more likely that they will accept the offer. Another example of a mediator from the Book of Why is the operation of a smoke alarm. A fire causes a smoke, which in turn triggers an alarm. If we have a smokeless fire, then the alarm will not be triggered. The third atomic structure is a collider. This is where two unrelated variables cause a third variable. In this example, we specify that the experience level influences the quality of your output, as does your workload. However, the experience level and workload are not correlated. So having specified the causal relationship using our causal diagram, in the third and final step, we aim to estimate the causal effect of a factor of interest. How do we do this? Well, to illustrate, we'll revert to the information provided in the Business Process Intelligence Challenge for 2017. In there, the company states a hypothesis that contacting the client multiple times causes them to decline the offer. However, in a couple of the winning entries in both the professional and the student category, they reckon that this is not quite founded. In fact, the winning student entry recommends chasing the customer. So the question is, does chasing the customer have a positive or negative impact on acceptance? And if so, how much? Before we proceed to showing how we answer the question, let's specify how we define whether a customer is chased or not. So first, we focus on incomplete offers where the customer hasn't sent in the required information. And we specify that a customer is chased if they're contacted 2 or more times without response. Otherwise, the customer is not considered chased. So, to illustrate, the bank sends the offer, the customer returns the offer. However, some information is missing. The customer is subsequently contacted 3 times. The chased attribute is true. Otherwise, it's not. So to determine the causal estimate, we revert back to our causal diagram. Notice the different colors. So we have some nodes colored pink, and those are the confounders. In this case, there's one confounder, the credit score. We also have a node colored yellow, and this is the intervention. This is the causal factor we want to estimate its effect. We might refer to it as the solution, but note that it's also called the treatment. This is because many of the causal inference techniques we use have their foundation in epidemiology, especially in investigating the contribution of a treatment to a patient getting better or not. The outcome is the variable that we are interested in influencing. In this case, that's whether an offer is accepted or not. Finally, notice that we have a causal factor that is labeled unobserved. What this indicates is that whilst we reckon this variable is an important causal factor, we don't have any data on it. In other words, we can't tell if a customer has been offered a loan by another company, but we include it in a causal diagram for completeness. So how do I estimate the effect of chasing a customer on the probability of them accepting the loan? We do this in a 3-step process. To do this, it'll be helpful if you are able to code in Python or R. But if you can't, that's not a problem. I'll post a link to a GitHub repository where the full code base resides in the comment section. However, for the purposes of this post, we'll focus on interpreting the results. Here is a snapshot of the event log with one application per row and the static case attributes. The objective of the initial score is to generate the propensity score for each case. The propensity score is the probability that a customer will be chased. Recall that this is the causal effect we're trying to estimate. If you recall from the causal diagram, the only confounder, that's the variable we need to control for, is credit score. So we create a logistic regression model which predicts the probability of a customer being chased based on the credit score. And here's the output of that model. Next, we calculate the inverse probability weight for each case. This is the measure of how odd or strange the case is with regards to the causal variable under investigation. I'll explain that further. Cases with a high inverse probability weight are cases that we expect to be chased. In other words, they have a high propensity score, but they weren't chased, or cases that we didn't expect to be chased because they had a low propensity score, but they were chased. Maverick cases, as it were. Conversely, cases with a low inverse probability weight are those that we expect to be chased, but were, or that we didn't expect to be chased and weren't. These are the boring cases. These tables show examples of cases with high and low inverse probability weights in our data set. The final step is to estimate the effect of this particular causal factor. And to do this, we use the inverse probability weights as weights in a regression model to calculate the causal estimate. So here you see the output of that model. That is the causal impact, and here is the confidence interval for that estimate. So let's revisit that exam question. Does chasing positively or negatively impact the probability of acceptance? If our causal assumptions are correct, we estimate it has a very small negative impact. And looking at the confidence intervals, even the best case scenario has a negative impact. But that's useful to know. The company may have changed its procedure to ensure all clients were chased. Think of how many hours this will have consumed. However, knowing the causal estimate provides insight that guides our decision making, because we know that this causal factor does not contribute to increasing the acceptance rate. And we could repeat this for other causal factors. Here we do that for offering the clients less than the amount they've applied for. As we expected, this also has a negative impact on the probability of acceptance. Notice this clause in italics though, provided our causal assumptions are correct. How can we validate whether or not they are? We'll answer that question in the next post of this series. Hope you join us.